Hi everyone, we're going to talk about distributed triangle detection. This is joint work with Assadi. Let's start by defining the local model of computation. This model was introduced by Lineal in 1992. We have a graph G with n vertices. Each vertex has a unique identity ranging from 1 to n. Each vertex can be viewed as a player. So in this example, the value of n is 8 and each vertex is a number from 1 to 8. So the vertices do not know the entire graph. What they know is just their local information, which is just the list of their neighbors. For example, 2 is going to be given a list containing 4, 6, and 7 as its neighbors. Vertex 1 is going to be given 8 as its neighbor, and so on. This is repeated for all the vertices in the graph. In addition to the list of their neighbors, they also have a source of randomness that only they can see, called private randomness. So how do these vertices process the graph? They are allowed to talk to each other over the edges of the graph. So in one round, any vertex can send any message of any length over all its edges. So one thing to emphasize here, the messages sent by a vertex need not be the same across the edges. Vertex 7 can send different messages to vertex 2 and 3. A protocol to process this graph can happen over many sequential rounds. And at the end of all the rounds, we want the vertices to output some answer about the entire graph in some distributed manner. And the aim here is to solve the problem, whatever we're interested in the fewest number of rounds. This is called the round complexity. The specific problem that we're interested in is just triangle detection. What we want from the vertices is if there is a triangle in the graph, we want at least one player to say yes. This player need not be a part of the triangle. By players, we just mean the vertices. If there is no triangle, we want all the players to say no, and that there isn't a triangle. So what do you do to solve this problem in one round? Let's do something very simple. A vertex is just sending its entire list of neighbors over all the edges. Vertex 2 now is going to communicate to vertex 7 that it has 4 and 6 also in its neighbor list. It's going to tell vertex 6 that it has 4 and 7 in its neighbor list. And now it's going to tell vertex 4 that it has 6 and 7 also in its list. So let's say all the vertices in the graph do this. At the end of this round of messages, all these players will come to know all the vertices in their two-hop neighborhood. For instance, 4 is going to come to know that 6 is in the two-hop neighborhood, and that there is an edge from 2 to 6 because vertex 2 would have sent this to 4. But if you know the entire two-hop neighborhood, then you have solved triangle detection because can be found just by moving away from you for only 2 steps. So triangle detection in this local model is very easy to solve. It is natural to ask what happens when we restrict the message length because we said that the vertices can send arbitrary messages of any length across all the edges. More specifically, we're restricting the message length to at most order log n over each edge. So this is known as the congest model, and this was introduced by Peleg in 2000. So solving triangle detection is not going to be as simple as what we did anymore, and we won't be able to solve it in just one round. So more generally, triangle detection and other subgraph detection problems are suited to study bandwidth constraints, or rather message length constraints, as opposed to locality constraints. The difficulty in solving the problem comes from the small length messages and not because we don't know beyond what is going on beyond our two neighborhood. So let's see what we can do in the congest model. How many rounds is it going to take to replicate the algorithm we had in the local model? In one round, since I have a budget only of order log n bits, we can send only one edge to the neighbors. So let's say vertex 4 is trying to do this. In the first round, it's going to send a message to 6 saying 2 is in my neighborhood. And in the second round, it's going to say 5 is in my neighborhood, and so on. So if you want to send the entire neighborhood, you are going to need order n rounds totally. So if you have order n rounds in congest, then you can solve the problem. So can we do better than order n rounds? It turns out we can. Izumi and Legal gave the first little of n round algorithms for this problem, and they gave a randomized algorithm that solves it in order of n to the two-thirds number of rounds. After a long line of work, Chong et al. Gave an algorithm that solves it in O tilde of n to the one-third number of rounds. And even for deterministic algorithms, again, after some series of works, we are able to match the guarantees of the randomized algorithms. And this n to the one-third number of rounds remains the state-of-the-art upper bounds. So another thing to note here, more details about all the results that I talked about, and generally for finding other cliques and other cycles can be found in this nice survey by Karen Senza-Hillel. It also contains other open problems in the area. And this is what we referred to when we were looking at this problem. So let's go back to prior work and now focus on lower bounds. Abood et al. Gave a lower bound saying that you need at least 2 rounds to solve this problem for deterministic algorithms. And Fisher et al. Later gave the same lower bound saying you need at least 2 rounds even for randomized algorithms. So in the original congest model, beyond these two lower bounds, we did not know anything. People have studied some weaker models that I'm not going to go into, but we do know stronger lower bounds in these weaker models. So the main question remains, can we actually get stronger lower bounds for this triangle detection problem in the original congest model, even for randomized algorithms? And just a reminder, here we're saying that we are allowed to send order log n bits per round per edge. There is a reason why there is such a strong gap between the upper bound and the lower bound. Eden et al. Showed that proving any lower bound of n to the alpha for some constant, for any constant alpha, is going to break barriers in circuit complexity that we don't know how to break now. So with such a strong barrier, it doesn't seem like we can actually get strong lower bounds. But can we get weaker and to the little of one lower bounds for this problem? And this is what we do. So our result says that the round complexity of this problem is omega of log n, even for randomized algorithms. And this is the first multi-round lower bound for this problem in the congest model. So I'm going to give a brief overview of the proof. The prior lower bounds for this, for not for this problem, but in this model for other subgraph detection problems, went through communication complexity. At a very high level, the lower bounds have this structure where there are two people, Alice and Bob, and the graph, the vertices of the graph are partitioned between Alice and Bob. Few edges are going to be present between the vertices in either partition, and these edges are going to be known to both Alice and Bob. The vertices inside Alice's partition will be known only to her, and the vertices inside Bob's partition will be known only to Bob. So we can relate hard communication complexity problems to congest protocols, and this gives lower bounds against problems in congest. What are the lower bounds we can get via this framework? We can actually get strong lower bounds for detecting peak leaks and P cycles for P to be at least 4. Some of these lower bounds are even tight, for example, for 4 cycles and for 4 cliques and odd constant cycles. So we are able to get strong polynomial lower bounds for other subgraph detection problems. So why does triangle detection, why can't we do this for triangle detection? What goes wrong? The simple thing is, however we partition the vertices of any triangle, there's going to be at least one player between Alice or Bob, so that the two of the vertices of the triangle are going to be given to this player. And once this happens, Bob will literally be able to see all the edges of the triangle. So the existence of the triangle is going to be known trivially. It is not hard to find triangles in this model. Even if we partition the graph among more players, it is not hard to see that you can still solve triangle detection very easily. But we're starting with communication complexity tools. So what else can you use from communication complexity? So maybe there are other tools that you can use to prove lower bounds specifically for triangle detection. And this is what we end up doing. Our main tool is round elimination. And in the context of communication complexity, this was introduced by Milterson, Nissan, Safra, and Wigderson in 95. Round elimination has also been used to prove lower bounds in the local model. And these two things have, they're very different in techniques, although the overall structure, which I'm going to describe, is the same. So our round elimination is much more similar to the Milterson et al. Framework than the local round elimination technique. So roughly, these are the steps to prove a lower bound. We want to construct a family of hard distributions, dr, dr minus 1, and so on till d0 recursively. So we will believe that graphs sampled from dr are going to be hard to solve for r round congest protocols. So let's say that this is not true, that there is a protocol which gets graphs from distribution dr and solves them with low communication over the edges. Then we would use this protocol to get another protocol which uses r minus 1 rounds instead and solves hard instances from distribution d r minus 1. So this protocol would still have the too good to be true property, or whatever we thought was not possible for hard round protocols. It will not be as good. We will have some losses, but it will still be too good to be true, and we will believe that this is not possible either. And we will continue doing this all the way till we get a zero round protocol. And this protocol will do something non-trivial, which it can't do. And this will give a contradiction. So let's focus on the first step for now. What is the family of hard distributions we work with? So for zero round hard distribution, this just means that the distribution is going to be trivially hard if the vertices don't talk to each other at all. There are just three vertices, and each of these edges between these vertices is going to exist independently with probability half. So what happens in these graphs is the vertices will not be able to guess without talking to each other whether a triangle exists with probability better than 7 over 8. So this distribution is going to be hard without any communication between the vertices. But even if they have only one round, they will be able to talk to each other and solve graphs from this hard distribution very easily. Now let's see how we can construct the one round hard distribution using the zero round hard distribution as the base. So for the one round hard distribution, what we will do is take each vertex from the zero round distribution and flood it with a lot of outer useless vertices. What will end up happening is, even if the vertices have one round to talk to each other in, the green vertices will not be able to communicate any information about each other because none of them will know what are the other green vertices. They will just see a list of neighbors and they will not know which ones are from the zero round distribution and which ones are the outer useless vertices we added. But this hard distribution is going to be easy to solve in two rounds because the outer orange vertices will know that they are not a part of the smaller instance because they only have degree 1, and they will be able to tell the other green vertices to ignore them in the first round, and in the remaining one round the green vertices can talk to each other and figure out if there's a triangle. But what we can do to construct two round hard distributions is repeat the same idea. We will take the one round hard distribution and flood it with outer useless vertices again. So our two round hard distribution is going to look somewhat like this. Let's recap again why such a distribution is going to be hard to solve for two round protocols. So all the highlighted vertices will not be able to say anything useful in the first round of communication because all they will see are a lot of pink vertices that were added to confuse them, and they won't know which ones are green or orange. But after the first round, the useless vertices we added will be gone because they'll be able to communicate to the green and orange vertices that they only have degree 1 and they are not important. The vertices will now have only one round to talk to because the first round is over. The green vertices will be confused now and they won't be able to say anything to each other because all they will see is a bunch of vertices and they won't know which ones are green and which ones are orange. After this second round is over, the orange vertices would be gone because they will now have degree only 1 and they'll know that they are not important. And you're left with this final round hard instance. But the first two rounds were useless anyway, so you're effectively solving the zero round hard instance without any communication, which we said would be hard. So how do you generalize this to construct hard distributions for R round protocols? So let's take an instance IR minus 1, um, which is a graph sample from the hard distribution for R minus 1 rounds. And each vertex from this graph IR minus 1 is going to get poly and NR minus 1 many new neighbors. So it'll see a lot of pink vertices, and NR minus 1 will be the total number of vertices in IR minus 1. The main thing to note here is the identities of the new neighbors and the identities of the inner vertices will be random and indistinguishable from each other. So every inner vertex will just have this perspective. It will see some k, which is poly in nr minus 1 many neighbors. And among these, some of them will belong to the ir minus 1 instance. But V is not going to know which ones among U1, U2, and so on belongs to the ir minus 1 instance because the identities of all the vertices will be random and is indistinguishable. What we'll be able to show is we will not be able to say anything useful to the IR minus 1 instance neighboring vertices because it doesn't know which ones they are. So just to recap here, this is the hard instance for R rounds. We're going to call this IR, and this is how we construct it. Each inner vertex from IR minus 1 is going to get poly and NR minus 1 many new neighbors, and the total number of vertices is going to grow by a polynomial factor. So we've covered this first part of how we're constructing these hard distributions and also talked at a very high level about why we think these distributions are going to be impossible for R round protocols to solve. The next part is to do the actual round elimination. And this is the main technical challenge that we had to overcome. So we want to take a too good to be true R round protocol, which solves distribution dr and use it to construct an R minus 1 round protocol that takes as input graphs from distribution dr minus 1. I am not going to say many details on how we get the smaller round protocol. I will just say this. So normally when we use this round elimination technique from Milterson et al. To prove a low bound for some problem, the first round messages have low correlation with the smaller R minus 1 round hard instance, IR minus 1 that we are trying to solve. This is not the case for congest protocols. There are two kinds of correlation that we deal with. The first one is the correlation between the messages and the inner round instance. So whenever a message is sent between two vertices, this reveals that the underlying edge is present. This is very much correlated with whether the underlying edge is present or not. The second kind of correlation is correlation between the messages sent by one inner round vertex. So this inner round vertex, for instance, can just pick a random bit from its private randomness and add this random bit to all its messages. This will create a lot of correlation between all the messages that this particular vertex sends. So the message edge correlation and the message message correlation are both present here. This is our main technical contribution. We give a multi-step sampling process that deals with this correlation using information theoretic tools. And this will allow us to get a smaller round protocol. We will briefly look at why we get the log n lower bound by just looking at the parameters. So for the one round, we get a lower bound of omega of n1, where n1 is the total number of vertices from the one round hard instance. The two round lower bound will still be omega of n1, but now the number of vertices will be n2, which is n1 to the c for some large constant c. So n2 to the 1 over c communication will be needed. If you continue this all the way till round r, omega of n1 will still be the communication lower bound, but now nr, which is the total number of vertices in the r round hard instance, will be n1 to the c to the r for some constant c, which was the polynomial blow up factor. And n1 is going to be nr to the 1 over c to the r. So if r is little of log n, this communication required is going to be little omega of log n, which is not something that congest protocols will be able to deal with. So we get a lower bound of omega of log n for solving triangle detection. I am going to conclude now. The main result we showed is that round complexity of triangle detection in the congest model is omega of log n. And the main technical tool was the round elimination framework of Milterson et al. And we dealt with a lot of correlation between the first round messages and the in round instance. We adapted this round elimination protocol for the point-to-point aspects in the congest model. What are the remaining open questions? So the main question is, of course, to actually improve this lower bound. So can we get a log n lower bound? We said that it is not possible to get into the omega of 1 lower bounds because this breaks current circuit complexity barriers. I will give a little bit more detail on these circuit complexity barriers now. So what Eden et al. Shows is if we prove an n to the omega of 1 lower bound for this problem, then we get an explicit function where circuits with log depth will need superlinear size. The current size lower bound we can prove is 3.1 times n on n bit inputs. So we are still very far from proving superlinear lower bounds. What we observed is just by changing the parameters a little bit, even an n to the omega of 1 over log n lower bound for this problem implies the same and gives us superlinear size lower bounds for log depth circuits. More importantly, we also show that any omega of log to the c n lower bound for some large constant c could also imply circuit lower bounds. Again, just by switching the parameters a little bit, there is nothing technically new here. So it is conceivable that some congest algorithms get better, which would mean that even a log to the c and lower bound for some large constant c gives the same superlinear size lower bounds for circuits. So with this connection to circuit complexity, we think that log n is the best lower bound that we can hope to get with the current techniques. What are some other open questions? We still don't know complete answers for detecting other cliques. For any constant p which is at least 4, we have an upper bound that says you can detect p cliques in n to the 1 minus 2 over p rounds. And we also have a lower bound that says we need omega of square root n rounds via two-party communication complexity. For p at least 5, there is a gap between this upper bound and lower bound, and we know that this gap cannot be solved by the current two-party communication techniques either. So it'll be nice to see if our techniques can actually resolve this gap. This is all I had to say for today. If you're interested in more technical details, you can refer to this TCS Plus talk, and you can find it at this tag. Thank you for listening.